Embedded systems, not something you hear often, but we actually use it in our everyday life. These are hardware systems with software that are designed for a specific purpose, either individually or within a larger system. Where can you find it? To name a few, we have smartwatches, traffic lights, pacemakers, pretty much most complex electric devices. These systems are often open to physical attacks where their functions could be manipulated. To prevent such attacks and protect critical information in operations, various hardware security or cryptography modules may be applied, which must undergo testing and validation on its security requirements before the product's market release. In Canada, this validation is carried out by the Cryptographic Module Validation Program. Today, we are carrying out one of the program's tests by building an integrated platform to test, break, and validate side channel security of the implementation of advanced encryption standards by collecting the power consumption traces and using statistical tools to analyze them.
AES is a secure communication technique that takes plain text information and acts numerous transformations on these plain text values in order to get a secure encoded ciphertext, with the intent being that the only way to decode this cipher is to have a special key that only trusted individuals should have. These transformations all require different power levels. By capturing traces of these power levels and using some math, we'll be able to find that special key and be able to decode any encoded ciphers that use that key.
We have used a target board that is specifically designed for understanding side channel power analysis. There were two options to collect the power trace. The first is by using an oscilloscope to collect power consumption data directly from the target board as shown in the video. The second one is by using the built-in analog to digital converter chip and the OpenADC interface of the main board to collect the data. These traces are collected and analyzed using differential power analysis.
This graph displays the amount of power consumed by the chip while executing the cryptographic algorithm. Not much to see here. Next, we're able to apply the correlation coefficient to determine the correct key. More traces means more accuracy. On the left, we only have 50 traces, and on the right, we have 200 traces. From there, we're able to plot the maximum correlation across all the different key guesses to quickly identify the key. Looks like we have a winner here. Next, we look at the measurements to disclosure. How many traces do we really need to find that key? And in this case, the answer is not very many. Looks like about 15 traces. Finally, we look to assess the protection of our implementation through test vector leakage assessment. We're looking for a value less than 4.5. Unfortunately, this implementation has a value nearly 200, meaning that it's not at all protected. If you're interested in seeing the code, check out the Git at the link below.